Welcome to ePathshala lecture series in computer science, and this is a course in cloud computing. In this module, we will discuss about consensus and paxos. So, today's learning objectives are the first is that we will look at what is consensus in a distributed environment, and then we will look at consensus in an asynchronous system specifically, because that is what really is the troublesome point, and we will look at the point that paxos is a solution for this, and we will see how paxos is used in cloud, who is using paxos in cloud, followed by summary. So, consensus is nothing but agreeing to do something together. When there is a group of participants, agreeing to do it together is called consensus. Let us take an example of an automated spaceship. This is a very complicated machinery where many parts are there and many computers are working together, and typically we would not like to keep this is a real time system, and we would not like to keep one controlling computer, one master slave relationship where one computer will take the decision on its own because of the timing restrictions. So, all these computers have to coordinate with each other to ensure that they have the overall workings. Now, in case there is a certain problem, or in case they have to decide whether to go ahead or to abort, how do they decide? They will talk to each other and they will communicate with each other, and together they have to take a decision. So, therefore, they need a consensus to proceed or to abort, not only to in case of a problem, but at every step they need to talk to each other, communicate with each other and decide. So, in distributed systems we see many group activities, mutual exclusion where we have to access a critical section. We need to update, there are backup servers and we need to update these backup servers. Maintaining a list of participants in peer-to-peer computing, there will be a list of participants and each participant has to maintain this list, and dynamically this list will vary. When there are many similar or equal participants and one of them will have to be chosen as a leader, even when we send a set of messages to a group of processes. These are many group activities, they all can be looked at as a consensus problem. So, if there are n participants in a group, then each will propose a value. So, we need to come to consensus that all of them will agree to one final value. We will stick to binary values, that means 0 or 1, yes or no, proceed or abort, but this can easily be extended to, this model can be easily extended to non-binary outputs also. All participants have to agree to one particular value. So, why we discussed the earlier examples in ME, in mutual exclusion, who is going to be the next one. So, there are many processes who are waiting to enter the critical section. Which process will enter the critical section is a consensus. In update and backup servers, if there are many values with which the servers have to be updated, what is the sequence of these values using which server will be updated? In maintaining a list in a dynamically changing environment, at any point of time t I, what is the list that each one has, and they have to agree on the same sequence of values. Among many similar nodes, one has to be elected as a leader. Each one may be proposing their own names, or each one may be choosing someone else, and that is not done. So, all of them have to agree to one particular value. Even sending a message, set of messages have to be ordered, as we have seen in reliable multicasting. So, all these is a consensus problem, and some consensus mechanism must be applied. So, formally, if there are n processes in a group, each process P has two variables. One is an input which can be 0 or 1 and an output which is initially undecided. The goal is to ensure that all processes will output the same value, either 0 or 1. There is a constraint that the output cannot be changed many times. So, we only change once the output, and from undecided it goes to decided with one specific value, and this value every process must be proposing the same value. So, whatever happens before that, finally I will choose one output, and that output should be identical or the same for all the processes. So, here are the assumptions that n nodes there will be one binary input and the nodes may crash, no guarantee of non-failing nodes, only the correct nodes have to agree to the output and all correct nodes values should be identical. The first property says agreement, correct nodes must output the same value, validity that all nodes, if initially all correct nodes have proposed the same value, then the output must be the that particular value, and termination says that all correct nodes must decide on an output. It cannot remain in an undecided state. So, what are the possible solutions? The first solution is that if I select a leader, if I elect a leader and that leader proposes a value and everybody accepts the value. Here the problem is the leader cannot fail. So, therefore, no processes should fail is an assumption for this particular mechanism. But what in a real environment we cannot assume that, therefore, leaders may crash. If a leader crashes, then there is no other way of coming to a consensus. And we may think that so what, we will elect another leader, but think of a consecutive leader crashes and we may never be able to, all other processes may never able to come to a consensus. Let us look at a second solution. Each correct process will propose an initial value and each correct process will collect the others proposed values. So, if I have proposed 0 and 5 other processes all have proposed 1, then it will continue in rounds, and at the end of f plus 1 rounds the algorithm will terminate and all correct processes will be given the output. So, in each round of this f plus 1, what will happen? Every process will collect all other n minus 1 processes values, and I will create a set, and all new values that I have received from the last communication, I will again in the next round I will forward only those values. So, communicate that set of values that it has not sent in any one of the previous rounds. Each round will be completed by setting a timeout. So, I start a round, I wait for n minus 1 inputs to come in, and when I have received n minus 1, I add my value and I have a set. I check from on the earlier set and I see that whether I have not sent any value earlier on, and I propose that I send that value to the next f plus 1 rounds, where we have this f is the failure, number of failures. If there are f failures, then f plus 1 round in a timeout bounded system perfectly works. Now, the problem here is what if I do not understand, when I receive a message from a process, I do not understand whether this is a response of the pth round or p plus 1th round. That means, if this system does not have bounds on message delays, does not have an upper bound on the clock drift. So, if someone's clock is drifting much faster than others' clocks, that may cause a problem. Maximum time for a machine to complete a process, a step in a process. No boundaries, no such boundaries. If we do not have such boundaries, we call this an asynchronous system, and in an asynchronous environment, consciousness does not have a solution. So, we looked at three situations. First, there is no fault. That is the easiest, and we can easily find a solution. In fact, the solution in case there are no failures is even trivial. A synchronous environment where I have a bound on my amount of time I take to decide on an output, amount of time a message takes to be received. Therefore, I can put a timeout and call it, decide that a process has not sent me an input because the process has crashed. So, at the end of the timeout, I decide that message would have been received, but because the process is faulty, has failed, therefore, the message is not going to be received. I can distinguish a faulty process. That is my synchronous environment. It is a well defined rounds and with a timeout, ended by a timeout. And we see that asynchronous system where the bounds are not maintained, there I cannot distinguish between when one round has to end and when the next round has to start, and there is no solution that is possible in such environment. So, this is called an impossibility in a consensus environment. In April 1985, authors Fisher, Lynch and Patterson, they published a paper. Till before 1985, it was assumed that consensus is a solvable problem. Only in 1985, they published this paper, Impossibility of Distributed Consensus with one faulty process. They showed that it is not possible to have a solution for such system. This is known as FLP theorem. So, why we are bothered in a cloud environment? Why we are bothered? Many applications will run in servers, and data of these applications will be in different data centers. Replicated data and replicated computation is necessary for making things fault tolerant in different data centers, in different clouds. So, to the consumer it appears to be one single point of access. On the other hand, the users are also spread in different locations, and they will collaborate with each other from different places to access their computation and data. So, in all these, if there is a network failure or if there is a node failure, then it is not possible to come to a consensus. So, consensus is required at every step in cloud, because different parts of the same task is being done in different locations, but in presence of failure, we do not know, and because cloud is consists of both synchronous and asynchronous environment, we cannot have a consensus in cloud. So, consensus in asynchronous system is possible only using paxos. This is the most popular consensus solving algorithm. It is invented by Leslie Lamport, as we have mentioned earlier, that he is a pioneer in many things, including inventing paxos. But even paxos does not guarantee that consensus will be reached because of the FLP theory, because theory says it cannot be reached. However, it provides what is known as safety and eventual liveness, which is sufficient for most of the systems. So, in cloud, many systems use paxos, such for example, Zookeeper, Apache Zookeeper, Google Chabi and many other systems. So, let us look at what is paxos. Paxos is a mechanism for achieving consensus. It guarantees that the nodes will choose only a single value in the end. All the correct nodes will choose only a single value, but it does not guarantee that if majority of the nodes have failed, then a consensus will be reached. So, paxos has its own limitations, however, that is the best option, and for all practical purposes it is absolutely working. So, what are the safety properties of paxos? Only a value that has been proposed by one of the correct processes will be chosen, some outside values will not be chosen, only a single value will be chosen, and a process can never learn that a value has been chosen unless it actually has been chosen. So, eventually the correctness will be restored. So, in some future it will be correct, that is the assumption that paxos uses. So, paxos uses many rules. Proposer who have the job of proposing a value for the purpose of agreement, and then it sends that proposed value to all the other processes. It sends it to a set of processes called acceptors. These acceptors have the job that they have to decide whether to accept a value or not. So, they look at all proposers values and decide on one, which is obviously the maximum. Each acceptor chooses a value independently. The acceptors do not need to talk to each other, they independently choose it, and many receive multiple proposals, each from a different proposer, and sends its decision to the learner. So, there is a third set of processes which are called learners. They are responsible for deciding whether a value has been accepted or not. So, proposers propose and acceptors accept and sends it to the learners. The learners will decide whether the specific value is good enough to finally accept or not. For a value to be accepted by paxos, a majority of acceptors must have chosen the same value. And paxos describes the action of its process by the roles of all these. All processes will be part of these and it will choose. So, in basic paxos there are 4 types of messages. One is called prepare PN, where PN is a number. A proposer may be initiated by a client, which is the user, would send a message to enough number of acceptors, which are the majority, or it is also called a quorum. A ready message will be sent by an acceptor in response to a specific prepare message, and then an accept, please accept, will be sent by the proposer to all the acceptors once more. If it has received the promises from the acceptors, it will send an accept message, and if it is acceptable by the acceptor, it will send a accepted message in which it will say that okay, this is the one I have accepted. So, this algorithm, it comes in 2 phases. In phase 1, step 1, proposal is sent by sending a prepare Pn equals to k, some value it will decide which is larger than all the values seen by this particular process which is proposing it, which is a proposer. And then the proposal promise in response to a prepare Pn, that acceptor may send a ready message with the last accepted PNN value thereof. So, it does not send necessarily a ready message. If it does send a ready message, ready message comes with a promise that so far you are the largest message that I have seen, and it sends the last seen largest value. So, so far it would have sent ready to someone else. Now, this proposer's value is bigger, larger. So, it is sending to this proposer that yes, I am ready to accept it, and this is the last value that I have seen. In phase 2, the proposer sends an accept request. The proposer says, okay, you please accept this particular value. Now, what value is sent by accept will depend on how many values the acceptors had sent to the proposer. And finally, the acceptors will send an accepted message if they have not received another prepare Pn equals to Z, where Z is greater than K and have not sent a ready message to that particular process. But if it accepts the corresponding proposal, then it should register the value. Now, its own accepted value will be Pn and V, and it will send it to the particular proposer. So, here I have the two proposers A and B and 3 acceptors X, Y, Z. First, A sends a prepare message with a value of 8. It sees 8 to be the largest number ever seen by A, and it sends a message prepare 8. If in X highest propose is 8, Y highest propose is 8 and Z highest propose is 8, they all send a ready message. Because there was no message earlier in them, they don't send any they don't send to the proposer any message, but they simply send a ready message. In the meantime, B sends a prepare 9 message, and assume that the message is not received by X because there was a failure. So, Y and Z receives the prepare 9 message, X does not receive a prepare 9 message. Now, Y will look at their highest value, 9 is bigger than 8 and 9 is larger than 8. So, therefore, what they will do, they will send a ready message to B. Now, assume that A has received the ready message from XYZ, it sends an accept message, accept 8 M1, because nobody has sent a value to A. So, it assumes some value M1 and it sends 8 M1 and 8 M1, 8 M1. Similarly, since X has not seen anything higher than 8, it accepts and it sends an accepted message. Similarly, B will send 9 M2, and since Y and Z have not seen bigger than M2, bigger than 9, it will send accepted 9 M2. A will now send another value, because A has not received reply accepted message from YZ. A will try again. It will send a prepare 10 message to everybody. Now, these two have 9 M2, this has 8 M1. They will now send 8 M1 and 9 M2 and 9 M2. A will say accept 10 M2. This is the 10 message and M2 is the largest value, and all will accept 10 M2. These messages will go to the learner and learners will decide. There are many types of paxos, many variations in paxos algorithm that are available. Now, in cloud, Google Chubby extensively uses it. As we have already seen, Chubby is a fault tolerant system used by Google. There are instances or cell per data center, and Bigtable, GFS, they all use this. In this, it has 5 replicas, and they need to keep these replicas similar or identical. So, database is replicated in Google's Chubby. So, Chubby client will propose a value to the proposers, and it will go through a paxos like mechanism to decide whether the value is acceptable or not. It is a master based environment. If a master fails, then again another paxos like mechanism will be used to elect a new master. So, this is how it decides, elects a replica to be the coordinator or the master, then coordinator selects a value and broadcasts it to all the other replicas which are the acceptors, and consensus, paxos like consensus is run, and if a consensus is reached, then the majority of the processes of the 5 will be accepting the value. Similarly, Apache Zookeeper is an open source project of Apache. It has a coordination system. It implements consensus service, again based on a variation of Paxos. It is not truly Paxos, but it is a Paxos like mechanism that they use to make the replicas consistent. Twitter uses Zookeeper. Within Twitter, the service discovery is done using Zookeeper. It registers, services register themselves in using Zookeeper, and clients query the production cluster for a specific service, and they will maintain an up to date host list for each service, and whenever a new capacity is added, these are added. This whole thing in Zookeeper happens using a paxos like mechanism called ZAB. To summarize this module, we looked at the consensus protocol, and we saw that how consensus is useful in a distributed environment. We saw that consensus is not possible in asynchronous system due to a theory called FLP theory. Paxos is the nearest possible or the most successful possible solution to consensus problem in asynchronous environment, and hence in cloud it is extensively used. So, we looked at the basic paxos, and we looked at an algorithm of basic paxos, and we saw the two cloud tools specifically we looked at. We looked at Apache Zookeeper and Google Stubby, and saw how paxos have been used and implemented. There are many other tools in cloud which use either these two tools or they use an independent paxos based tool. In the next class, we start with what is virtualization, which is a very important mechanism in a cloud environment. These are our references. Thank you.